All right, well, good morning, everybody. Hope everybody had breakfast. If not, you can still, I think, grab breakfast either outside or downstairs in the expo hall. So today, we'd like to welcome Ryan Chipman. Ryan runs our SQL Engines team. He's going to tell us all about Atlas SQL. Please hold questions until the end. We will have, hopefully, 3 to 5 minutes towards the end. And also, don't forget to rate the session on the app. Okay? With that, any further ado, Ryan.
All right, thank you so much. As Sig mentioned, my name is Ryan, and I'm a director of engineering here at MongoDB, responsible for our SQL Engines team. So the SQL Engines team builds products that allow our users to connect their MongoDB data to BI tools, or more generally, just issue SQL queries against their MongoDB data. I'm guessing maybe you're here because you heard the Atlas SQL announcement in the keynote yesterday and wanted to learn a little bit more. Maybe some of you are existing users of MongoDB's BI connector and want to understand what the relationship is. Or maybe you just saw SQL in the agenda and are curious to find out why a company so strongly advocating for the document model is talking about SQL. If any of those describe you, I hope you're going to find some answers to your questions during this talk today. So I'm here because I want to talk to you all about the future of SQL at MongoDB. Let's chat about what that looks like. So in the past, SQL experiences with MongoDB usually started with downloading some third-party software. In the past, this might have been a third-party driver from Simba or CData. More recently, with the BI connector, you still have to download MySQL client software to connect. In this future of SQL at MongoDB, the drivers and connectors that you use are developed, maintained, and distributed by MongoDB. In this future, your SQL queries work seamlessly with the document model. You can see and query your data via SQL as it actually exists in your MongoDB collections, not just in a format that's been stripped of its structure and polymorphism to fit into the traditional relational model. Finally, in this future, the SQL queries that you're going to write are in a dialect that is compatible with the SQL 92 standard you and your tools are already familiar with, but extended for ergonomically querying your structured data in MongoDB. As you've probably guessed, I'm happy to share that this future I'm describing is available today. It's called Atlas SQL, and it is a brand new MongoDB native SQL experience now in preview. So today, we're going to talk in a bit more detail about what exactly Atlas SQL is. We're going to compare it with the BI connector, MongoDB's existing SQL offering. I'm going to go into a bit more detail about the Atlas SQL type system, which I personally think is one of the coolest technical details of the Atlas SQL system. And then finally, I'm going to take a few minutes to give you a sneak preview at what's ahead for Atlas SQL in the next 6 to 12 months. So without further ado, what is Atlas SQL? Starting from the left, we can see the first of 4 components that make up Atlas SQL. So Atlas SQL is not a single piece of software. In fact, it's multiple software components that span the entire software stack between your Atlas data and your BI tool. The Atlas SQL interface on the left is a new $SQL aggregation stage and schema management APIs that have been added to Atlas Data Federation. Next, we have the SQL Dialect that you use when you issue $SQL queries against Atlas Data Federation. This dialect is SQL 92 compatible, but it also provides first-class support for MongoDB data types, polymorphism, and structured data. Moving to the client side, we provide custom SQL drivers built specifically for Atlas SQL. These drivers wrap the MongoDB native language drivers. They provide an experience that should be familiar to anybody already working within the MongoDB ecosystem. We have a JDBC driver available today, and we'll have an ODBC driver coming soon. Finally, all the way on the right, we have our BI tool connectors. So these are wrappers around the SQL drivers that provide the configuration and UI needed for the smoothest possible BI tool connection experience. So we've talked about what the components of Atlas SQL actually are, but to get a better sense of how they all fit together to make up Atlas SQL as a whole, I'd like to spend a few minutes talking about how a query issued by a BI tool like Tableau might make its way through the system. So let's imagine, for any of you who are familiar with Tableau, that this is a query you've written as a custom SQL query on top of a data source. If you're not familiar with Tableau and don't know what this means, that's also OK. You won't need to understand it to understand the demo I'm about to give. So Tableau is going to start by making an execute query call to the JDBC driver. This just immediately returns a result set, which is basically the JDBC equivalent of a cursor with some extra goodies tacked on. The first thing that Tableau is going to need to do is it's going to need to understand the shape of your query's result set. This is how it knows what dimensions and measures to show you when you go to actually build your chart in the tool. JDBC provides the getMetadata API call for this. When our custom JDBC driver receives the getMetadata method call, it's going to issue a SQL getResultSchema command to the Atlas SQL interface. Atlas SQL will compile the SQL query and use type inference to deduce the shape of the result set without actually executing the SQL query. It returns the description of this result set as a JSON schema to the JDBC driver, which will translate it into a result set metadata object and return it to Tableau. At some point, Tableau is going to want to actually get the results of your query. And when it's ready to kick off this process, it's going to iterate the cursor for the first time using the next method. When this happens, the JDBC driver is going to issue the SQL query against the Atlas SQL interface using the $SQL aggregation stage that we've created. This query is going to be compiled into a standard MongoDB aggregation pipeline that we send to Atlas Data Federation so it can execute it against your Atlas cluster. The result of this query is sent back to the JDBC driver by way of Atlas Data Federation. And finally, the JDBC driver will expose the results to Tableau via the result set cursor. So just to step back and summarize for a minute, we've talked about all the components that make up Atlas SQL. We have the Atlas SQL interface. We have the custom SQL dialect that we have built for Atlas SQL. We have our SQL drivers, which allow you to seamlessly connect your BI tools and other software to the Atlas SQL interface. And finally, we have the BI tool connectors, allowing you to use your BI tool of choice for the easiest possible connection experience to MongoDB Atlas. Next, we're going to compare Atlas SQL with MongoDB's existing SQL offering, the BI connector. So at a fundamental level, the BI connector and Atlas SQL are trying to do the same thing. They're trying to allow you to connect your MongoDB data to your SQL-based BI tools or SQL queries. However, the details of how they accomplish that goal differ significantly. And in the following slides, I'm going to explain some of these differences, and I hope they're going to help you understand why we've decided to build something new instead of just iteratively improving upon the BI connector. The first difference that I'm going to talk about is an architectural one. The BI connector is a proxy server. It implements the MySQL wire protocol on the front end, and it talks to MongoDB in the back end. Atlas SQL, on the other hand, is a library that is embedded within Atlas Data Federation. And we believe that there are a couple advantages to this architecture. First, from an engineering perspective, it allows us to spend more of the team's time and effort building the features that actually matter to all of you. Better query compilation, new features in the SQL dialect, JDBC and ODBC drivers, more BI tool support, as opposed to the BI connector, where we had to spend a significant amount of time and effort maintaining a MySQL wire protocol implementation, or all of the networking and plumbing code that's necessary to keep a proxy server running smoothly and securely. But beyond just the engineering considerations, the biggest benefit of the embedded in Atlas Data Federation architecture for Atlas SQL is that any tool within the MongoDB ecosystem that can speak the MongoDB wire protocol can take advantage of Atlas SQL. So Atlas SQL is now taking SQL out of its MySQL-shaped bubble that it has lived in the past and bringing it into the MongoDB ecosystem at large in earnest. The next key difference between the BI connector and Atlas SQL is how they handle structured and polymorphic data. So because the BI connector is an implementation of the MySQL wire protocol, it's constrained by the set of features and concepts that actually exist in MySQL. Unfortunately, this set of features and concepts does not include structured or polymorphic data. So the BI connector has to find a way to get rid of your structured and polymorphic data before it returns data to MySQL client software. This is unfortunate for a couple reasons. First of all, your structured and polymorphic data in MongoDB is probably modeled that way for a good reason, and you lose the richness of your MongoDB data model when you view that data through the BI connector. Second, this flattening and unwinding that the BI connector does to morph your data into a traditional relational format also comes at a performance cost. Every query that you might issue against a collection that contains structured or polymorphic data is prefixed by conditional projections or unwinds that, at the very least, slow down your query incrementally and may even prevent it from using indexes on the source collections. Atlas SQL, on the other hand, supports querying your structured and polymorphic data as it actually exists in the collection in its original form. Users who still wish to see a flattened or unwound version of their data, of course, are still going to be able to do so by using the flatten or unwind table functions that we've added into our custom SQL dialect. But the key difference here is that we do not force SQL users into a less rich and less performant view of their MongoDB data. Another important difference is the SQL dialect that you're actually going to use when you're writing queries against each of these products. So both dialects share a common base of functionality, which is the functionality required by the SQL 92 specification. But the ways in which they diverge from the SQL 92 specification are important. Atlas SQL, when it diverges from SQL 92, tries to do so in a way that stays as close as possible to the semantics of the underlying MongoDB aggregation primitives that we are eventually going to compile your SQL query to. The BI connector, on the other hand, has to faithfully emulate MySQL's behavior for any query that we might issue to it. And the problem is, in many cases, that MySQL behavior is either difficult to implement performantly as a MongoDB aggregation pipeline or sometimes hard to implement at all. So by taking advantage of the increased semantic flexibility of the Atlas SQL dialect, we're going to be able to generate more performant MongoDB aggregation translations. Now, I want to mention that this performance doesn't come for free. The BI connector is still a very mature product that has a lot of performance optimizations built in. And it's going to be one of the team's top priorities to make sure all of those performance optimizations get ported over to Atlas SQL. But the key thing that our custom SQL dialect does is it raises the ceiling for performance of Atlas SQL queries relative to what we could get with BI connector queries. The final key difference between the BI connector and Atlas SQL that I want to talk about today is the difference between third-party and first-party client software. So I mentioned earlier that when you connect to the BI connector, you have to do so using MySQL client software, which is developed by the MySQL team, not by us here at MongoDB. So when the BI connector was a new product, we actually considered this to be an architectural advantage. It allowed us to spend engineering time on the then unsolved problem of translating SQL queries into aggregation pipelines. But it's been many years since then, and now the problem of SQL to aggregation translation is largely a solved one. And today, the biggest pains that we hear about from BI connector users are related to configuring and connecting from that third-party client software. Because it is third-party, there is often very little or nothing that we can do to alleviate that pain. In Atlas SQL, because we own the entire software stack from client to server, we will be in a position to solve that pain and to provide the smoothest possible connection experience from your SQL tools to your MongoDB data. Okay, so I want to stop for another quick summary. So we've talked through some of the key differences between the BI connector and Atlas SQL. We talked about some major architectural differences. We talked about how they both handle structured and polymorphic data. We talked about the difference between the MySQL dialect and Atlas SQL's new custom SQL dialect. And we talked about some trade-offs between first-party and third-party client software. I now want to take the talk in a slightly more technical direction, because I consider Atlas SQL's type system to be one of the coolest and most innovative parts of the whole Atlas SQL platform. The way that we model types in the compiler for the Atlas SQL dialect is unique in the industry, and I believe it's one of the key factors that allows us to successfully combine the worlds of MongoDB and rich data models with the SQL traditional relational world. In particular, I'm going to highlight two key aspects of the Atlas SQL type system: static typing and structural typing. Static typing is when you use type information at compile time. This is in contrast to dynamic typing, which is when you use type information at runtime. C and Java would be examples of programming languages that are statically typed, whereas Python and JavaScript are dynamically typed. In the world of query languages, most SQL dialects are statically typed, whereas MongoDB aggregation is dynamically typed. A structural type system is a static type system where types are distinguished not by some name that they're given when they're declared, but rather by their structure, by what properties they contain or what methods they have. In the programming language world, one of the most popular structural type systems is the one that you find in TypeScript. Talking about query languages, most SQL dialects do not have a structural type system because despite being statically typed, a lot of them don't even have a concept of structured data. MongoDB aggregation isn't really structurally typed because it is not even statically typed. Atlas SQL has a static structural type system. In the next few slides, I'm going to talk about what this actually means in practice and hopefully explain why I think this is such a powerful combination. Let's start with static typing. What does it actually buy us? One of the key benefits of static typing is that it allows us to perform type inference at compile time. Among other things, Atlas SQL uses type inference to deduce the schema of a query's result set without actually executing that query. And this might sound familiar. We just talked about how Atlas SQL uses this to implement the SQL get result schema method in the Atlas SQL interface. In fact, without static typing, it would be effectively impossible for us to correctly implement the JDBC get result set metadata method because we'd have to iterate through the entire result set of the query and empirically observe the schema, which is impractical to say the least. The next benefit of static typing is that it allows us to provide some really important guarantees. In particular, we can promise you that an Atlas SQL query will not error at runtime as long as the schema information that we have about the collections is correct. So this is incredibly useful, especially for analytics queries, which tend to be longer running queries. Nobody wants to come back after an overnight query or a long weekend and discover that their batch job actually failed 20 minutes in because of a typo or some unexpected polymorphism in their data. Static typing is what makes this guarantee possible because it allows us to error ahead of time if there's any possibility that a query might fail, instead of erroring when we actually run into the problematic data. Now, you can imagine that there might be some cases where all this compile time checking might actually become more of a hindrance than a help. You can imagine, for example, there might be some situations where you, as a human, know some things about your data and your query that the compiler isn't quite clever enough to figure out, and it doesn't let you run a query that you know should be valid. In these situations, it would be nice if you could tell the compiler to back off and fall back to the dynamic typing that MongoDB's underlying aggregation primitives have, instead of the Atlas SQL static type system that we are layering on top. In fact, the Atlas SQL compiler is capable of doing this internally today, and we hope to take on a project soon to expose this functionality to end users. This will allow end users to have the best of both worlds: static compile time guarantees for your long-running analytics queries that you want to be confident in, and the quicker, more expressive, easier to iterate dynamic typing when you just want to type a few queries and get a quick feel for the shape of your data. So let's switch over to an example. We've talked about a lot of these benefits in the abstract, but I'd like to show you what it looks like in practice. Let's imagine we have the following collection. We have fields A and B, which are integers most of the time, but sometime around, say, the millionth document, the field A starts becoming a string instead. If we run the following MongoDB aggregation pipeline, which tries to add fields A and B, it's going to return a first batch and return many more batches, not actually erroring until you encounter that millionth document. If instead we consider this analogous Atlas SQL query, which is also trying to add fields A and B, this query is going to fail immediately as soon as you issue it, as long as we have schema information that is telling us all of the information we discussed earlier, that field A can be an integer or a string, and that field B has to be an integer. Basically, the compiler will look at the types and say, OK, I know how to add integers to integers. I don't know how to add integers to strings, so I have to error because this query might fail at runtime. Now, where does structural typing come in? Structural typing works in combination with static typing. In particular, one of the key benefits of the structural typing is that it enables us to provide these compile time guarantees even in situations where we don't know everything about our collections. And this is crucial for making Atlas SQL useful for all kinds of expressive MongoDB data models. MongoDB's data modeling functionality is fundamentally more powerful than the data modeling capabilities that you have in traditional relational databases. In particular, you can have a MongoDB schema where, for example, you don't actually even know what all the possible fields are, or the set of possible fields can change dynamically over time. In these kinds of schemas, relational databases just can't model them. And MongoDB aggregation language can allow you to query these kinds of schemas, but it does so with dynamic typing. It doesn't provide these kinds of ahead-of-time static guarantees about your queries. Atlas SQL's structural type system allows us to use the information that does exist about a schema, even if it's not complete, and still provide as many compile time guarantees as possible. Let's again take a look at what this means in practice. Consider a collection that is described by the following JSON schema validator. We have an _ID field, which is an object ID when it exists. But beyond this, we don't actually know whether there are any more fields, or if they exist, what they're called. But we do know, and this is the additional properties part of the JSON schema right here, that if any other fields exist, then they must be integers. This is a perfect example of the kinds of schemas that just can't be modeled at all in traditional relational databases. But Atlas SQL is actually able to execute the query that you see here, trying to add fields A and B, despite the fact that it doesn't even know whether field A or field B might exist. The way it does this is the compiler will look at A and B, and it'll say, I know A is either missing or an integer, and I know B is either missing or an integer, and it's safe to add missing values, safe to add missing values to integers, and it's safe to add integers. So we can execute this query and indeed guarantee that it will not fail at runtime. All right, so with the little bit of time that remains, I want to step back away from the technical details and talk a little bit about what's ahead for Atlas SQL in the next 6 to 12 months. Starting on the left, the very next thing that the team's going to be working on, actually starting as soon as next week, is building an ODBC driver. As I mentioned before, we have a JDBC driver available today, but having both ODBC and JDBC drivers is going to be a requirement in order to make Atlas SQL usable from tools across the entire SQL client ecosystem. After we've built an ODBC driver, we're going to move on to supporting more BI tools. We have Tableau support available today, but we'd also like to add support for Google's Looker, Microsoft Power BI, and maybe some workbench-style tools like dbeaver or MySQL Workbench. These will only be the beginning. We hope over the years to add support for many, many BI tools. Finally, looking a little bit further ahead into 2023, one of the things on our radar is also making sure we provide an excellent Atlas SQL experience for handwritten queries. A lot of the use cases that we've been talking about and focusing on so far are BI tool use cases. Users are actually dragging and dropping in a GUI tool, and the SQL is generated by that tool behind the scenes. However, this isn't the only use case that we want Atlas SQL to be excellent for. Anyone who's typing their own SQL query should also be able to take advantage of all of the benefits that we've been discussing today. We haven't quite decided what exactly we're going to do to make the handwritten Atlas SQL query experience excellent, but some things that we're considering are adding some SQL query helpers, or maybe even an interactive SQL subshell into the MongoDB shell. But that being said, this roadmap is tentative, and it's going to be driven by customer requirements that we actually know about. So the one request that I have for all of you here today is to go to Atlas Data Federation, set up an instance, try running some SQL queries, and then reach out. Tell us what worked, what surprised you in a good way or a bad way, and tell us about the workloads that you want to run on Atlas SQL, because these requirements will be a huge part of us prioritizing what we can build to make your SQL experience an excellent one. Thank you, everybody, for taking the time to come to watch the talk. With whatever time remains, I want to field any questions that anyone might have. And before we start answering, I'll just also say that if you think of something later on or don't get your question answered here, you should stop by the analytics booth where you will find either me or someone else from the SQL Engines team to answer your questions or give you a demo. Thank you.
Thanks, Ryan. Question from the audience?
That was a great talk. Thank you.
Thank you.
Two questions for the handwritten SQL and other stuff that you already have. Do you use Apache Calcite by any chance?
So all of our query compilation and execution infrastructure is built in-house at MongoDB. So the SQL query compiler that compiles your SQL query into an aggregation pipeline is built from scratch by the SQL Engines team. And then the actual execution infrastructure for that query is Atlas Data Federation, which is also built within MongoDB. So it's all first-party products.
Okay. So a quick second question. Atlas Data API, what exactly is it, and what's the overlap with the SQL piece?
I might not be the best person to answer the question, but I'll give it my best shot. I believe Atlas Data API is something that makes your Atlas data accessible via an HTTP API. And right now, that is a separate product from Atlas SQL, though there's no fundamental reason why maybe they couldn't be unified in the future if we cared to.
I think the API lets you run any aggregation, so you could use a $SQL stage, I imagine. And if that's not possible, it would be relatively easily to implement.
More questions?
Any option for the on-premises MongoDB? Like, we don't have the cloud MongoDB, and we do need the SQL on our BI tools.
Absolutely. This is a use case. Just to repeat for the room, the question was about an on-premises version of Atlas SQL. This is a use case that we're very much aware of and is actually going to be one of the first things that we're thinking about architecturally after this preview release is what is the future of on-premises SQL for MongoDB. Atlas SQL is intended to be the successor to MongoDB's BI connector, so we do plan to have some discussions about what on-prem looks like going forward, but we don't have any answers yet, unfortunately.
Thank you. So currently we are using Snowflake in our place. So we can see when we are running a long query, we can see the data pane, the query plan, that how the query is running, what are the bottlenecks, and also a suggestion that how can we improve on that. Is there something similar we can expect in MongoDB as well?
So this might be a question that I could hand over to someone from Atlas Data Federation. And I'll actually refer back to one of the things I discussed during the talk, which is because Atlas SQL is embedded in Atlas Data Federation, none of this is something that we have to build specifically for Atlas SQL. Anything that Atlas Data Federation or MongoDB Atlas builds around the kind of tooling that you're discussing or any other features are things that are available to you by default, even if you write SQL queries instead of MongoDB aggregations. So I don't know about about those kinds of features specifically, but someone from Atlas Data Federation can definitely answer those questions for you.
Two questions. The first is how much overhead between this additional compile into the aggregation pipeline overhead added there? And second question is, will you plan to build a tool similar like a Studio 3T? You can just write the SQL and the extractor. Yeah. So because currently like Compass can only accept the aggregation pipeline, so will you also build some similar tool? Okay.
So the first question was about the overhead of compiling SQL queries into aggregation pipelines. So the actual overhead of compilation is very small. It's a pretty quick process because we have all the information we need available statically to turn an aggregation pipeline into, or turn a SQL query into an aggregation pipeline. There's also a little bit of overhead associated with writing aggregation pipelines that have the correct SQL semantics, but that is not itself necessarily overhead. It's actually just writing a query that behaves the way it's expected to in the SQL world. As for your second question, integration with tools like Studio 3T or Compass, we don't have anything today because it is just the preview release, but I expect that some sort of deeper integration with Compass would be on the horizon.
I want to ask you about, you have a gap filling function. You're talking about if you're basically typing, let's say, an integer field and there's some missing values. Do you have any types of like validation checks to make sure that basically what you're guessing at filling in doesn't throw a query like way off track?
So The feature that you're describing sounds a little bit to me like MongoDB's new Densify feature. This isn't something that's built into Atlas SQL today by default. If you wanted to use this functionality with Atlas SQL, you'd have a couple options. You could create a MongoDB view that uses Densify to achieve the gap-filling behavior that you need, and then run SQL queries on top of that view. Or also, because Atlas SQL uses a dialect that we build ourselves, if this is a feature that's important to you, definitely talk to us, because it's possible that we could choose to expose this Densify functionality through the SQL dialect itself as well.
In the current BI connector, the schema on Atlas, the schema is auto-generated, and the users, or as a developer, you have no control over that schema, okay? And it has certain problems that come of that. You've mentioned the schemas in going to Atlas SQL. Is there any control over that schema, or is there anything that's addressed or different in that, in regards to that?
There is, yes. So by default, Atlas Data Federation will generate a simple schema by sampling that describes your collection, but the Atlas SQL interface does provide commands for getting and setting a schema for a collection. So unlike Atlas BI Connector, you are able to fix schema problems yourself.
Okay, I think that's the last question, probably.
You said that the problem of translating SQL to MQL is largely a solved problem right now. Who did you mean specifically that solved it? MongoDB itself, or is it some independent players or open source projects that you meant?
Solved by MongoDB. Specifically, the SQL Engines team, over the course of developing the BI connector, went from a place where it actually wasn't possible to translate all SQL queries into MongoDB aggregation to today it is for all of the SQL queries that we support in the BI connector and Atlas SQL. And this was via a combination of effort from the SQL Engines team doing the R&D on the translation itself, and MongoDB's query team expanding MongoDB aggregation with whatever features we needed to be able to correctly model a variety of SQL queries.
And are you aware of any open source projects that successfully solve this problem?
I am not aware of any open source projects doing that, but I'd be curious to hear them if anybody does.